welcome to the principles of metal cutting section. We are now proceeding to some of our interior to it, how we study some of the basics of principles of metal cutting. Basically, if you see, the metal cutting process is considered to be the severe plastic deformation process. Normally, plastic deformation comes in the metal forming. However, the metal cutting is a subtractive process. If you see, the manufacturing normally or introductorily you can divide into 3 or 4 sections, where one is the metal cutting, metal forming, advanced machining processes, and joining processes, and casting, and also so on. So deformation comes under metal forming. However, this particular metal cutting process is considered to be the severe plastic deformation process. If you see the stress strain graph of any ductile material, normally here given is the mild steel. Basically, if you see the basic curve of the stress strain, if you see, the metal cutting starts after the plastic deformation. Okay, so that's why here also deformation is taking elastic region, then the plastic upper yield point, lower yield point, and ultimate point, then the fracture point comes. So the metal cutting starts after this position. Okay, so that's why this process is normally called as a severe plastic deformation region, or severe plastic deformation process. Okay, so in the mechanics of machining, you can study more about these deformations, what are the other things, the mathematics behind it, and these are the courses already taught by some of the people, and currently also some of the people are teaching. So that comes in the completely mechanics, how the mechanics deals with this process and all those things. Since this is an introductory, so we can see that how and what is the introduction part of this one. See, the basic thing that one has to remember is, in the metal cutting operation, the workpiece should be softer than the tool material. That is, the tool material should be much harder than the workpiece material. Okay, so that can be thing, but at the same time, if you are increasing the hardness of your workpiece material, it will become difficult, because the hardness ratio, that is the hardness ratio, is nothing but the tool hardness to the workpiece hardness. If the hardness ratio is near or similar region, then metal cutting will be slightly difficult. So that's why the hardness ratio should be slightly higher. Normally it can range from 3 to 5 to so on. Okay, so if the hardness ratio is very high, the forces and all those things also slightly lesser. The tools which can resist these forces is the resistance of these forces by the tools is slightly higher. So that will be good cutting process. The cutting forces increases with increasing the yield strength of the material, that workpiece material. If you see the yield strength of the workpiece material in the previous slide, if the yield strength increases, if you see here, yield strength of this any material increases. If it goes higher, what will happen? The forces will be required will be very high. So, or it increases. That's why the metal cutting process is good if the material's yield strength is less. But if at all, if I want to machine the higher yield strength materials, normally I have to choose appropriate tools whose hardnesses or yield strength and other properties are much higher. That is what the first point says. The second point, harder materials difficult, already explained you. If the workpiece is much harder, there is another concept called hard turning operations or hard machining operations, where it is difficult to machine because the tools there are very low varieties of tools ranging from HSS to the diamond. So you have to choose among those. So if you want to machine a CBN, you don't have any much alternatives. because the CBN itself is one of the hard materials. So it is slightly difficult. Okay, so for what I mean to say is it is easy to machine the less harder materials. Usually with the increase in the cutting velocity, the cutting forces reduces or decreases. This what I mean to say is this is particular to those material. If you see here, in case of high thermal conductivity materials, okay, what will happen if the workpiece material is, assume that this is the workpiece material, the conductivity is very high in this one. What will happen if I am cutting with high velocity? That means that cutting velocity, what will happen? The workpiece rotates at very high speeds. If it is rotating with high speeds, the temperature generation in the high velocity cutting or high speed cutting will be very high. If the conductivity of this material is very high, what will happen? The temperature conducts at a faster rate. So thermal softening takes place ahead of or slightly ahead of the cutting tool. So in that circumstances, the cutting forces reduces. That is what I mean to say. Now I just want to show you a video where machining of ductile and brittle materials can be shown. You can, in this video, you can first see what is metal cutting and what is the ductile materials metal cutting and what is the brittle materials also. In this video clearly shows the difference between a ductile material cutting and the brittle material cutting and all those things.
Workpiece material is removed in the form of chips. Continuous chips are formed when the...
You can see here, this is the continuous chips cutting. Okay, so you can see there is no discontinuity, but the thing you can see, the only thing that you can observe here is on the bottom side. So at the bottom side means if you see that the top side, normally this is the top side. This top side is tool in contact with the chip. On the bottom side, you can see the rough surface of the chip.
Cutting tool is in continuous contact with the part, especially when cutting ductile materials such as soft steels or aluminum. A discontinuous chip is formed even in a continuous operation like turning when the material is not.
You can see here, this is the brittle materials machining. The cutting tool is cutting the brittle material. In this one, the material removal is taking or the fracture is taking place slightly ahead of the cutting tool itself.
Ductile enough to deform continuously. It fractures ahead of the cutting tool. Discontinuous chips are formed when machining brittle materials like cast iron.
Okay, just now we have seen the video. What is the difference between metal cutting of brittle materials and ductile materials? So now we will see what is the basic things that we have observed in the video. Okay, the machining of brittle materials, normally chip separation takes place and affects brittle fracture. Okay, so in the brittle materials metal cutting, the what will happen? Chip separation affected by the brittle fracture requiring less energy. Normally, this is subjected to some materials only like cast iron or something. Okay, so brittle fracture, it is taking slightly ahead, because of which there is no the chip flowing on the rake surface and all those things. So the temperature generation is slightly less, because of which the point is partially valid, that is less energy in the chip formation. The shorter chips causing the less frictional force, because the continuous chips in the ductile materials causes lot of friction because it flows on the rake surface, which you can observe in the upcoming slides, and there is no built up edge formation. You can see the built up edge formation in the upcoming slides. So normally the best material or the basic material for the introduction purpose, you can say, is cast iron is one of the good examples that one can see as a brittle material machining. If you see the ductile machining, it has a very good effect that is called a smooth and continuous cutting process. It is a smooth and continuous process because of which there is a heavy chance or 99% you will always get a continuous chip formation. If you have a continuous chip formation, the cutting tool experiences uniform load. In a brittle materials, whenever you see a brittle fracture here, in the brittle fracture, what will happen? It is, you cannot say that it is a discontinuous process, but in a nano scale or a micro scale, you can say this is a slightly discontinuous process because it the particles will hit or the surface which is coming may hit. So it is subjected to the papers to paper. Some of the papers they express this, and the basic problem in the continuous process is built up edge formation. What is the built up edge formation and all those things you will see in the upcoming slides, which may affect the surface finish. What is the problem is, if the built up edge formation takes place, this forms on the surface of the workpiece, or that means that the workpiece or the product that is coming out. So it hampers or the worse, make worse the surface finish. At the same time, continuous chips will entangle there in the machining region itself, which also may rub against the final product. This also causes the worsening of the surface finish. If you see the mechanics of chip formation, see this is the workpiece and this is the tool. You can see here the tool and this is the chip. Okay. So this T naught represents the uncut thickness and TC represents the chip thickness. Normally red on red you cannot see this one. This is called the chip thickness, and this is called the T naught is the chip uncut thickness. This is the normally the rake angle. Alpha stands for rake angle and phi stands for shearing angle, and this is called the flank or clearance angle. You can see clearance angle and all those things. Okay. So this is about the two-dimensional metal cutting process. Normally it is called as the orthogonal metal cutting. Most of the cases we just simply assume our metal cutting process as a orthogonal metal cutting process and we proceed. Okay. The shear zones. There are three main shear zones in this metal cutting process. If you see the metal cutting operation here, this is taken from our own research papers. The metal cutting is, whenever the metal cutting takes place, you have three shear zones. In the shear zones, whenever we see there are three shear zones, this is a picture that we have taken from our own research or just from our laboratory. So if you see the metal cutting operation, the tool, this is the tool, this is the tool and this is the workpiece. There are three shear zones. One is the primary shear zone. Normally primary shear zone, if you see, this is the primary shear zone where workpiece and chip in between, it is along the direction of the shearing region. Okay. So secondary shear zones is between chip and tool. This is nothing but secondary shear zone. The red one which I am already showing, this is the primary shear zone, this is the secondary shear zone, and this is the tertiary shear zone. The tertiary shear zone is between the final product or the after machined workpiece to the tool. This is the tertiary shear zone. The chip formation, normally the separated material flow on the rake surface of the tool is called as a chip. Okay. This is the basically the chip that is flowing on the rake surface. Okay. This is a chip, and normally the chip can be measured, or you can study this by using many things. Normally one of the methods is moving camera technique and by giving the grids on the surface. what we can do is some of the techniques are there, just you just do the gridding, place the grids on the surface and you just move and you can study, or some of the quick stop mechanisms also there. You just quickly or this mechanism just stop it, and at that position you can also study the deformation of the chip process. This is how about the chip formation and the different types of chips. Basically this is another basic study where you can see the four types. Normally some of the basic textbooks, if you see, they only deal with three. One is continuous, and continuous chips with built up edge and discontinuous, and there is another one which is I am going to deal is serrated or segmented chips. So there are four varieties. This is called the continuous. There is no break or something, it just moves continuously. Okay, so this is called the continuous chip. Whenever you are machining a ductile material, whenever you are, the second variety is the continuous chips with BUE. BUE stands for built up edge. Okay, so the built up edge you can observe clearly here. This is called the built up edge formation. Okay, so this will hamper partially the cutting process. That is what. And the third one is segmented or the serrated chips. So there is a slight variation between the discontinuous chips and serrated chips. So in the discontinuous chips, normally in schematic views, they can show like there is a discontinuity between two, these are the segments. But however, in the serrated chips, you can see normally each and everything there is no this one, but however there is a discontinuity after some time. So that is a slight difference. Normally in the older textbooks you may not find, but in some of the research papers you may find this, or some of the new textbooks you may find that there is a slight boundary between discontinuous, this is wrong, discontinuous and serrated chips. So we will just deal what are the things that causes the continuous chips. If you see the continuous chips, favorable conditions, first and foremost is workpiece should be the ductile material. Okay, if it is ductile material, smooth cutting will take place, and the cutting speed should be slightly higher, that is high speed, so that the continuity will take place. At the same time, low feed and depth of cut. If you have low feed and low depth of cut, the cutting will be smoother and the forces experienced by the tool will be very less. At the same time, our cutting edge will remain sharp for longer time, and high back rake angle. Normally back rake angle, if your back rake angle is very high, assume that my single point cutting tool is like this. So this is called my back rake angle, alpha B. So if my angle is very, as angle increases, what will happen? My chip flows smoothly on it. So that is what the beauty about this high rack angle. But the problem is, or the good things is, or the bad things about this is, surface finish will be very good. That means the roughness is very low. So you may get a good shiny product out of this one. Low power consumption, because of the continuous cutting, there is no intermittent or some other problems. So less power is required and tool life is more. These are the advantages of continuous chips machining of ductile material, which generates the continuous chips. The second thing is continuous chips with built up edge. Here also the material that you do with a workpiece material is ductile material, but the difference only with the machining conditions here, that is low speed. In continuous you might have seen high speed and high feed and high depth of cut. These are the two changes between continuous and continuous with BUE. Okay, if you input these two conditions, normally what will happen, this built up edge formation takes place. You can see a droplet type of thing. This is nothing but the built up edge. After the built up edge, if you see, if you are cutting continuously, the built up edge will also adhere onto the chip, which we don't bother about much because it won't come under the product, because our product is this one, whatever which we are getting here. So this built up edge will deposit. It is not going to affect our product, but however, it is going to affect our tool rake surface. This is our tool rake surface. It may damage the tool rake surface, which may lead to the crater wear and all those things. The other disadvantage of built up edge formation is this built up edge partially will adhere onto the product also. So this may deteriorate the final product quality. So that's why we normally don't want this built up edge during the machining process. That's why in order to impart, we have to select these two conditions such a way that BUE should be minimum or BUE can be reduced. So the effects more to life. Normally some of the papers they say that the built up edge that is forming here, you can see the built up edge forming here will protect the tool from the direct contact of the workpiece in a nano range or a micro range. That means there is a slight gap between the cutting tool as well as the workpiece machining point. Okay, and the surface finish is poor. The surface finish is poor. Since why I mean to say is, I was saying the more to life because there is a gap. This is the cutting point and this is the my cutting tool position or the point. There is a gap. This is a gap. So here my built up edge is protecting my tool. That is how the tool life is more. The second point is surface finish on the workpiece basically will be poor. You can see the surface finish is poor because we need a better surface finish for a good quality product. If the built up edge fragments are welding or it has adhering to this workpiece final product, then the surface quality will be very poor, so which we may not like. Unsteady cutting forces, because this is not the built up edge which is forming here is looks like a semi solid or a liquid type of thing, because of which this is a solid, this is also a solid, and in between you have a liquid or a semi solid. There may be chance whenever this BUE goes off or BUE formation may be less, at the same time BUE is going to the chip as well as BUE going to the final product, because of which there is a fluctuation of the size of the BUE, because of which there may be the difference in the distance between my cutting point and my workpiece real contact point. Because of this there is a slight fluctuation and this may lead to unsteady cutting forces, but this may not be very huge, but there is a slight variation in the cutting forces. A high power consumption, because built up edge helping the adhesion on the rake surface. If you see the built up edge, the built up edge is adhering on the rake surface, it is adhering on the final product also, because of which what will happen, the friction between my rake surface and the chip, the friction between flange surface and the final product goes up. So if the frictional force goes up, what will happen, power consumption also goes up. If you see my required is force is F is required to useful cutting force plus unuseful or the frictional. Because of this built up edge formation, what will happen, our frictional force goes up. That means my required force goes up because this is increasing. That's why the high power consumption. takes place. This is with comparison to continuous chips, not that we required very high power or something, just relatively to the continuous. In a built up edge we need slightly higher power. Okay, so this about this one. So the third one is segmented or serrated chips. These are non-homogeneous chips and semi-continuous. There are discontinuous, but these are semi-continuous. That means that you will neither it can be a continuous nor it can be a discontinuous. In between that, normally you will get. So low thermal conductivity and high strength exhibit this behavior. If your thermal conductivity is low and strength of the materials will be low, then this behavior exhibits and associated with difficult to materials and high speeds. So discontinuous chips, normally discontinuous chips are very common in brittle materials like machining of silicon carbide or any other glass material or some other materials. Or for example, the common example is cast iron. If you are machining the cast iron, normally you will get the discontinuous chips, and the favorable machining conditions is low speed and high feed and high depth of cut and low back rake angle. Okay, these are the things. What I mean to say is, if your speed is low, your temperature generation is also low. If you are high feed and high depth of cut, what will happen in a cast iron? Whenever you do this one, what will happen? It will lead to the particles type of chips. That is what the discontinuous. These are very good from the operator point of view or operator safety point of view. In a continuous chips, basically the chips entangle there itself. Once the assume that my cutting on the cutting tool chip comes, what will happen? This curls it there, and it may touch the workpiece and it may destroy it. For that purpose, sometimes the operator, what he tries to do it, he want to pull it out so that it won't affect or it won't damage the final product. In that circumstances, it may hamper or it is slightly dangerous to the operator, because it may, the chip is very sharp and very hard, so handling the chip is very problematic in that conditions, and it may hurt also. So that is one of the problems. So this is in that particular point, or for the operator safety, whenever you are pulling that high temperature and sharp chips, this is very good discontinuous from that point. So the effect, the surface finish is very good because there is a discontinuous, so there is no entangling of the chip on the final surface and it is not damaging. The more power consumption, as I said, if you are having a discontinuous, what will happen? It may, there is a micro or a nano level depend on your feed and depth of cut. So there is a slight discontinuity in the workpiece cutting region and the point or the line of the cutting tool. So there is a micro nano discontinuity will be there, because of the power consumption will increase. If the power consumption increases or discontinuity is there, what will happen? Every time it will touch in a micro nano. Whatever I am showing is very high amplitude region, but the thing is that there is this one cutting edge will regularly goes and touch, so that the tool life may reduce. This is about the discontinuous chips. Okay. So as I said, from the operator point of view, continuous chip is not good, because it may hamper the operator's hand and it is high temperature. For that purpose, the researchers come out with some of the alternatives, that is called, one of the thing is nothing but the chip breaker. If you see the chip breaker, okay, this is the alternative. Just on the tool, this is the tool, on the tool, you just have a chip breaker. Whenever the continuous chip flows on it, it will encounter here and breaks into the pieces. So that the beauty about this one is, in a continuous process or in a continuous chips, your process is generating the continuous chips. So your power consumption is low, you are getting a better surface finish. However, for the safety of the operator and to prevent the entanglement of the chips on the surface that is touching after machining, because of that, if you can put a chip breaker, you are converting into the discontinuous chips. So that is the beauty about it. This chip breaker is helping us in producing the continuous chips, which reduces the force required, indirectly power requirement, and gets a good surface finish. At the same time, for the operator safety point of view and entanglement of this chip on the final product and destroying the surface roughness of the product, we are making the discontinuous chips. So this is about chip breaker uses. However, there are other methods also which can break the chip. That is nothing but chips can also be broken by changing the tool geometry. If you can change the tool geometry, you can also choose the tightly curled chips. These are, you can see the tightly curled chips which are coming here, and chips with workpieces. If you have a straight here, if you see you have a straight, that means normally whatever you have seeing a zero rectangle, if you have a zero rectangle, normally curls are coming. If you can generate some geometry on the rake surface, you are going to get, this is called chip hit the workpiece and breaks. Normally, because of the slight geometry variation, what will happen, the chips are hitting the initial workpiece and they are breaking. So in another case, continuous chip moving radially away, here also this is a geometry. Normally this is one of the geometry. If you can generate another one, but here also the chip hits the tool shank. Here instead of the, in the figure B, it is touching the initial workpiece. Here it is touching the tool shank. Shank is nothing but this particular region, okay, and breaks off. So this, just you can play with the geometry of your tool where the chip is moving. Normally the chip moves on the rake surface, obviously. So if you play some geometry on that one, which can hit the initial workpiece, and it should not hit the final product. It should not hit my final product. Okay, it can hit my initial product which is to be machined, and another case you hit the shank of the tool and it can break. So these are the two conditions. So various zones in the tip to tool interface region, which we have seen recently. If we can change the geometry, and you can enhance the chip breakability. Similarly, if you see this, the beautiful schematic is done from the experimental point of view from our papers only. So this is a workpiece tool interface, as you can see here. So this is about the machining region, and the chip in the schematic, if you see, the chip is moving on my cutting tool, and because of which there is a sticking region and sliding region. Whatever the three-dimensional, normally whatever we are showing, this picture is a three-dimensional one, but we are seeing from top view, so there is no third dimension visibility here. So there are two regions, one is a sticking region and sliding region. So you can see this sticking zone and sliding zone. This is we have taken from our own laboratory experiments only for the demonstration purpose. So see, normally some of the things can be explained by doing some of the experiments at the workshop or in our laboratory, then teach according to that will always give good feel. So that is what the teaching is about. So it is a combination, you have to bring some of the research results to show better pictures. So in that way, if you see this picture, This is called chip tool interaction region. Normally this is continuously is nothing but the chip tool interaction region, where you have a sticking zone. This is sticking zone, and this is called a sliding zone. Okay, you can see it's a sliding zone. In a sticking zone, you don't find the upbraiding marks. These are upbraiding marks. You can see the chip is moving and it is upbraiding. That means that the chip is sliding in this direction and it creating its own marks. This is called a sliding region, which is shown by the blue arrow, and the sticking region, because of the sticking nature, predominantly you don't find the directional scratches on it. Instead of that one, you can see the material removal from the tool in the form of craters or molten material is gone out. So this is the difference between the sticking zone and the sliding zone for the given metal conditions. These are the metal conditions that we have given in the metal cutting operation to demonstrate in a better way to you people for understanding what is sticking and what is sliding region, in practically how it looks like and all those things. That was the motive for us, apart from publishing the similar works. So chip thickness measurements, normally chip thickness can be measured using direct method and indirect method. So direct method, normally you can take the micrometer or vernier calipers and you can measure it, but you may not get the exact value, because if you see, this is the cutting tool and this is the chip. Normally in a continuous chip or a segmented chip, you assume that this is a continuous chip or a segmented chip or discontinuous chip. What is the basic problem is, one side it is a smooth cut, this is a smooth cut, and another side it is very rough. So if I put a vernier calipers here and here, you may not get exact value, because from point to point the thickness is varying. So direct method is okay, but it may not give you exact value. If you have a sophisticated equipment, you may get it. In the case of other chips also, you can see there is slight variation on both sides. So it may not be easy to get. So the other method that you can rely on is, so for example, if you are cutting a known material, so you know density of the material. Normally density of the material is known to you. In the indirect method, what I mean to say is, you just take a chip from here to here. So you can take the chip and you know the density of the material, because the workpiece material, the density is constant. From here you can measure the length of the chip. Since there is a curve, you can use the thread and you can measure the L, and now you know length also, because you measured using a thread, and just you put on the scale and you take this curve is there, just put on the curve, and the curve length you just make it straight to the thread, then you put on the scale and you take the L, and you know the depth of cut. Normally depth of cut is assumed to be the width which is not visible in this one. So from the depth of cut, you know the width of the, okay, and this is taken, the length of the chip already measured. The same thing can be taken on a common balance and you can measure the weight or the mass of that one. See, you have already taken the chip out which having a length of L. You just use the common balance or the micro balance and measure the mass. So you know density equal to mass by volume, where you know the mass from the micro balance, density of a material is constant. Now the volume, if you see the volume, you know already length and you know width of that material. So only the thickness is not there, that is called length, width and thickness. sorry, okay. So this is the thickness. So you know the two things so that you can measure the chip thickness. This is how indirect method works. Okay, that's all about the today's class.